Outdoors, we rely on an invisible grid of satellites to plot our exact coordinates, navigating city streets by following a blue dot on a screen. But the moment you walk inside, that system breaks down. Steel framework, metal roofing, and thick reinforced concrete act as a shield, scattering and absorbing the faint microwave signals broadcast from space. For an average person, losing a cell signal in a basement is a mild inconvenience. But when police and paramedics cross the threshold of a sprawling high school, a multi-story mall, or a concrete office tower, they enter a communications dead zone. Back at the command center, the incoming data simply stops. Dispatchers are left staring at a frozen blip at the building's entrance, completely blind to where the responder is moving deep inside the structure. In an active emergency, losing track of an officer's position costs critical minutes. Operating indoors requires abandoning the satellite grid entirely and building a localized tracking architecture from the ground up. The foundation of that indoor system is a self-contained technology called inertial tracking, and it activates the second an officer walks through the doors. This diagram shows the mechanics of dead reckoning. Body-worn sensors act as a highly advanced pedometer and compass. They measure the physical length of every stride, register the exact angle of every turn, and calculate elevation changes on stairwells to draw a continuous map of the officer's path. But hardware inevitably drifts. If a sensor miscalculates a turn by a fraction of a degree, or misjudges a stride length by an inch, that microscopic error compounds. After a few hundred steps, the system is calculating a position entirely divorced from reality. Because internal sensors drift over time, they cannot operate in a vacuum. To maintain accuracy, the system has to check its math against physical infrastructure anchored inside the building. That correction relies on a network of Bluetooth beacons. These are low-power transmitters permanently mounted to ceilings and walls throughout a facility. When an officer walks past one of these fixed transmitters, their drifting inertial device pings the beacon. The system registers the interaction, verifies the beacon's fixed location, and instantly pulls the officer's digital track back to the correct coordinates. This effectively resets the map, but it comes with a strict limitation. Bluetooth technology only confirms proximity. It tells the command center that an officer is somewhere inside a specific classroom or corridor, but it lacks the fidelity to pinpoint exact coordinates within that space. If an extraction team is trying to locate an injured colleague through thick smoke or fallen debris, knowing the general sector isn't enough. They need a highly precise targeting layer. To bridge that final gap, engineers use ultra-wideband, or UWB, radio technology. UWB operates by transmitting rapid-fire pulses of energy across a very broad spectrum of radio frequencies. By timing exactly how long it takes for these pulses to bounce between devices, the hardware measures physical distances down to the centimeter. If an officer needs immediate extraction, their radio begins emitting these pulses. The incoming rescue team carries UWB receivers that lock on to that exact frequency, establishing a direct device-to-device connection that entirely bypasses the building's own network. This turns the rescue equipment into a localized, highly precise radar. It bridges the gap between knowing someone is trapped in a 50-foot corridor and walking directly to the specific inch of floor they are lying on. Gathering raw data from step counts, Bluetooth proximity, and UWB frequencies is only half the process. To execute a rescue, the command center needs a unified visual interface. This 3D digital floor plan serves as the canvas for the incoming data. By loading precise architectural blueprints into the tracking software, dispatchers monitor personnel moving dynamically across multiple stacked floors at once. If a responder goes down, their inertial sensors detect the impact or register a prolonged lack of movement and trigger an automated alert. The software pinpoints the incident on the 3D grid and instantly calculates the fastest, safest physical route to reach them. The digital map does the heavy lifting for the command staff, translating a chaotic web of overlapping radio signals into clear spatial coordinates. Consider how this layered stack performs in a crisis. An officer pursues a suspect deep into the sub-basement of a sprawling shopping mall, far out of reach of any GPS satellite, and sustains a severe injury. Their body-worn inertial tracker detects the unnatural velocity of the fall. The hardware scans the basement architecture, pings the nearest wall-mounted Bluetooth beacon and isolates the officer's exact sector. On the surface, the incident commander sees a flashing coordinate populate on the mall's 3D blueprint and dispatches the medical unit to that specific underground quadrant. As the medics push into the basement corridor, their UWB receivers pick up the downed officer's localized signal, guiding them directly through the darkness to the exact coordinates. There is no grid search and no clearing empty rooms. In a severe trauma scenario, survival requires immediate medical intervention. Wandering blindly through a complex, unfamiliar structure to locate a casualty consumes time that responders simply do not have. By layering internal motion sensors with external Bluetooth anchors and high-frequency radar, tactical teams carry their own infrastructure indoors. They ensure that no matter how complex the environment, command always knows exactly where they are.